In this video, C.3, we're going to look at how the critical mass is the mass of fuel needed for the reaction to be self-sustaining. The reaction being nuclear fission reaction, sort of like in our power plants that we have today. So this is an easy way to sort of visualize this. Here we have the subcritical mass. Now what we have here is showing a neutron bombardment hitting a uranium-235 nucleus, which is unstable. And then through that nuclear reaction, we know it splits into two other nuclei and then emits some more neutrons. And those neutrons encounter other 235s and then cause them to undergo fission, so on and so forth in a chain reaction. Now, what you see here is a lot of these neutrons, because of the size of the sample here, actually end up just leaving the sample and then thus not colliding and causing a subsequent reaction. So when you don't have enough of these collisions or bombardments happening, that means you have a subcritical mass. That means you may start the reaction, but it's going to fizzle out because there's not enough other uranium-235s around to keep doing it. What happens is you increase the mass to the critical mass. So you get a sample that's large enough that there are more uranium-235s, and thus you have a greater chance or enough probability that the reaction will be able to continue because there are other uranium-235s around to be bombarded with. So that is how, or that is why, in visual terms, you can see here why this works. We have many uranium-235s before some of them exit, but although some exit, there are still more inside that will still be hit by other neutrons. So it continues the chain reaction. We need that critical mass for it to be called self-sustaining.